In today's lesson, we're going to be talking about bounds. Let's say we have a set A, which is a subset of S, and A and S are ordered sets. So, there are two types of bounds. Let me explain the first one. For an upper bound exists if there exists an element B. Notice we write this element B. We denote it with the lowercase letter b, not the uppercase. And notice, so if there exists an element B, which is an element of this ordered set S, such that, so we usually denote such that with ST, such that there, for all elements A that are in this ordered set A, we know that there is B is larger or equal to A. So this is pretty self-explanatory. For instance, for this set A, which is an ordered set, we have 1, 2, all the way to 10. We know that an upper bound could be 11 because this number is larger than all of these elements. Or it could be 12. It could be 10.01. It could be 1,000. There are a lot of upper bounds. There are an infinite number of upper bounds for this ordered set A. Okay, what about lower bounds? Well, obviously, a lower bound is the exact opposite of an upper bound. For a lower bound B, there has to exist a B which is an element of S, such that for all elements A that are in this ordered set A, which is a subset of S, B is smaller or equal to A. So an example again would be this ordered set A, 1 to 10, and some lower bounds could be 0, 0.9, 0.99999, negative 10, negative pi, 0.1, and more. So again, there are an infinite number of lower bounds for this ordered set A. So, what are some examples where a set has no upper bound or no lower bound? An example would be this set here, Z, which denotes all integers. Now we know Z is from negative infinite to positive infinite. For instance, we can have ... all the numbers before this number here, negative 3, negative 2, negative 1, 0, 1, 2, 3, ... all the numbers larger than 3, up to infinite. So in this case, for any element, for any number, let's say, that is B, let's assume that B is an upper bound of Z. So what this means is for any element in Z, for any element A in Z, so A is an integer, we have that B is larger or equal to A. But obviously B is an actual number, like 1 million, 1 trillion, 1,000 trillion. And there will always exist this number, say A plus a certain number like N, that is going to be larger than B. Because the set Z includes all integers. So no matter what B is, it's a finite number, right? You can define it, you can write it down. But for any B, there will always be B plus 1, say B plus 1, or to be safe, B plus 2, the floor function of B plus 2, which is basically the integer part of B plus 2 if B is a decimal, that will always be larger than B. And this is actually an integer. So this set here, Z, which is an ordered set, has no upper bound. Similarly, we can prove that it has no lower bound by proving that for any B that we assume is the lower bound of Z, there will always be a smaller number, a smaller integer, say the floor function of B minus 2. That is going to be less than B, that is still an integer. So hence, not all sets that are ordered have upper bounds and lower bounds. Another example would be the natural number set, where this includes all the numbers from 0 to infinite. Well, this set has a lot of lower bounds. It has an infinite number of lower bounds, but it has no upper bound because its upper limit, there's no upper limit actually. Its upper limit is infinite. So thanks for watching.